Look up into a clear, moonless night sky, far from the glare of city lights. You will see it, a tapestry of pinpricks scattered across a velvet abyss. Some are brilliant, defiant beacons. Others are so faint they flicker at the very edge of perception. For millennia, we believed this was the extent of creation. A celestial sphere, a dome of fixed stars, placed there for our benefit. A comforting, finite ceiling above our world. But what if that ceiling is an illusion? What if each point of light is not just a distant fire, but a sun like our own? And what if the dark spaces between them are not empty, but are filled with other suns, other galaxies, so far away their light is lost in the immensity? This is the story of a journey to measure the immeasurable. It is a quest that shatters our sense of scale, our place, and our own significance. We ask a simple question, a question a child might pose. How big is the universe? But the answer is anything but simple. It is a story of paradox, of cosmic horizons, and a reality so vast it strains the very limits of human imagination. To truly grasp the answer, we must first unlearn everything we think we know about space, about time, and about the very nature of seeing. Our journey begins not with telescopes, but with geometry. 2,500 years ago, the ancient Greeks performed one of the first great intellectual leaps in cosmic measurement. They understood a principle called parallax. Hold your finger out at arm's length and close one eye, then the other. Your finger appears to jump against the distant background. This apparent shift is parallax. The closer the object, the more dramatic the jump. Greek astronomers, like Aristarchus of Samos, reasoned that if the Earth orbits the Sun, then the nearby stars should also appear to shift against the backdrop of more distant ones throughout the year. They looked for this stellar parallax, and they found nothing. Not a flicker, not a wobble. Their conclusion was logical, but profoundly wrong. They believed the stars must be relatively close, fixed to a single crystalline sphere, and that the Earth must be stationary at the center of it all. The truth was far more staggering. The stars were so mind-bogglingly distant that their parallax shift was too minuscule for the naked eye to ever detect. The universe was already proving itself to be vastly larger than our senses, or even our cleverest theories, could initially comprehend. For nearly 2,000 years, this geocentric, finite model held sway. It was a comfortable, human-centric cosmos. Then, thinkers like Copernicus, Galileo, and Kepler began to dismantle it, piece by piece. They placed the sun at the center of our local system, and in doing so, they demoted the Earth. But even they had little idea of the true scale of what lay beyond Saturn. The stars were still largely considered a shimmering backdrop to our solar system's dance. The real breakthrough in measuring the stars had to wait for technology to catch up with theory. In 1838, the German astronomer Friedrich Bessel finally succeeded where the Greeks had failed. Using a powerful new telescope, he measured the parallax of the star 61 Cygni. The shift was impossibly small, less than 1/3 of an arcsecond, equivalent to the width of a human hair seen from 60 feet away, but it was there. And the distance it implied was staggering. Over 60 trillion miles, or about 11 light-years. For the first time, a human being had wrapped a measuring tape around a star. The first rung on what we now call the cosmic distance ladder had been placed. The floodgates of cosmic scale were beginning to creak open. But even this colossal distance was just the measurement to our next-door neighbor in a city of stars we had not yet even recognized as a city. By the early 20th century, astronomers knew we lived in a flattened disk of stars, a celestial river of light we called the Milky Way. The dominant view, championed by the influential astronomer Harlow Shapley, was that the Milky Way was the time's entire time's universe. The countless stars we could see, the vast clouds of gas and dust, this was it. Everything. There were, however, some mysterious smudges in the sky. Faint, spiral-shaped clouds called nebulae. Shapley and many others believed these were just nascent solar systems, forming within our own Milky Way. But a few, like Heber Curtis, argued for a more radical idea. They contended that these spiral nebulae were in fact island universes, entire galaxies, just like our own Milky Way, but lying at unimaginable distances. The debate came to a head in 1,920 inches, what became known as the Great Debate. It was a clash of titans, a battle over the very size and structure of reality. But without a reliable way to measure the distances to these faint smudges, the debate ended in a stalemate. The universe hung in the balance, its true nature hidden behind a veil of uncertainty. To pierce that veil, science needed a new tool, a new kind of ruler. That ruler was discovered not by a famous professor in a grand observatory, but by a quiet, meticulous woman working as a human computer at Harvard College Observatory. Her name was Henrietta Swan Leavitt. Her job, for which she was paid a meager 30 cents an hour, was to catalogue the brightness of stars from photographic plates. She was not even allowed to operate the telescopes herself. Yet, in her patient, painstaking work, Leavitt noticed something extraordinary in a class of stars called Cepheid variables. These stars have a peculiar quality. They rhythmically brighten and dim over a period of days or weeks. Leavitt discovered a stunningly precise relationship. The brighter a Cepheid was intrinsically, the longer its period of pulsation. Think of it like a lighthouse. Imagine you see a lighthouse in the distance, but you don't know how far away it is. If you somehow knew it was a massive 1000 watt bulb, you could calculate its distance based on how faint it appears to you. Leavitt had found the cosmic equivalent of the bulb's wattage. By measuring a Cepheid's pulsation period, astronomers could know its true intrinsic brightness. By comparing that to its apparent brightness in the sky, they could calculate its distance. Henrietta Leavitt had handed science a standard candle, a ruler capable of measuring distances not in trillions of miles, but in millions of light years. She had forged the next, crucial rung on the cosmic distance ladder. The key to unlocking the universe now lay in finding a Cepheid variable within one of those mysterious spiral nebulae. The task fell to a brilliant, ambitious, and notoriously difficult astronomer named Edwin Hubble. Perched atop Mount Wilson in California, he commanded the most powerful telescope on Earth, the 100-inch Hooker telescope. Night after grueling night, Hubble aimed this colossal eye at the largest and most famous of the spiral smudges, the Andromeda Nebula. He took long-exposure photographs, searching for the telltale flicker of a Cepheid. In October of 1923, he found one, and then another, and another. He carefully measured their pulsation periods. Then, using Leavitt's groundbreaking period luminosity law, he performed the calculation. The result was earth-shattering. The number he calculated was nearly 1 million light-years. It was a distance so immense, so far beyond the known boundaries of the Milky Way, that it could only mean one thing. Andromeda was not a cloud of gas within our galaxy. It was an island universe, a galaxy in its own right, a sprawling city of hundreds of billions of stars, separated from us by a gulf of intergalactic space so vast that the light he had just captured began its journey when our human ancestors were still learning to master fire. In that single moment, the known universe expanded 100-fold, 1,000-fold, 1,000,000-fold. The ceiling of the cosmos had not just been cracked, it had been obliterated. Our galaxy was not the universe. It was just one of countless others, adrift in an ocean of unimaginable scale. Humanity was, for the first time, truly lost in the cosmos. But Hubble's work was far from over. As he measured the distances to more and more of these newfound galaxies, he began to analyze their light. He passed their faint glow through a prism, spreading it into a rainbow-like spectrum, and in these spectra, he discovered something profoundly strange. The light from nearly every galaxy was stretched, its spectral lines shifted towards the red end of the spectrum. This phenomenon, known as redshift, was a cosmic Doppler effect. Just as the pitch of a receding ambulance siren drops, the wavelength of light from a receding object stretches, becoming redder. What Hubble found was not just that galaxies were moving away from us. He uncovered a distinct pattern. The farther away a galaxy was, the faster it was receding. This was a revelation that would forever change our understanding of reality. The universe was not a static, eternal stage upon which galaxies floated. The universe itself was expanding. The very fabric of space-time was stretching, carrying the galaxies along with it for the ride. To visualize this, do not think of galaxies flying apart through empty space like shrapnel from an explosion. That is the wrong picture. Imagine instead a loaf of raisin bread dough rising in an oven. As the dough expands, every raisin moves away from every other raisin. A raisin close to you moves away slowly. A raisin on the far side of the loaf moves away much faster. Crucially, from the perspective of time's anytime single raisin, it appears as if all the others are rushing away from it. There is no center to this expansion. The expansion is happening everywhere, in the very fabric of the dough itself. In this analogy, we are on one raisin, and the distant galaxies are the others. The space between us is the dough, and it is continuously expanding. This discovery had a mind-bending implication. If the universe is expanding today, then yesterday it must have been smaller, and the day before that, smaller still. If you run the cosmic movie in reverse, all of the galaxies, all of space and time, all matter and energy must rush back together into a single, infinitesimally small, infinitely hot, and infinitely dense point. This was the inescapable logic that led to the theory of the Big Bang. The universe had a beginning. It has an age. And this finite age is the key to finally answering our question. It is the reason we must speak not of the universe, but of the observable universe. Because the cosmos has a finite age currently calculated to be 13.8 billion years, there is a fundamental limit to what we can see. Imagine standing in the middle of a vast, dark forest. At the moment of the Big Bang, a brilliant flash of light illuminated the entire forest. That light has been traveling outwards in all directions ever since. The light from trees 1 foot away reaches you almost instantly. The light from trees a mile away takes a few seconds. The light from a tree 8 billion light years away, if it had been stationary, would only be reaching you right now. Anything beyond that distance, any light that would have had to travel for longer than 13.8 billion years to reach you, simply hasn't arrived yet. It is still in transit. This creates a sphere of visibility around us, a cosmic horizon. The edge of this sphere is the most distant point from which light has had time to reach us over the entire age of the cosmos. This sphere is the observable universe. So, is the answer to our question simply 13.8 billion light years? Is the radius of our observable sphere 13.8 billion light years, making its diameter 27.6 billion light years? The answer, astonishingly, is no. The reality is far, far larger. And the reason for this brings us back to Hubble's expanding dough. The light from the most distant galaxies we can see did not travel through a static, unchanging space. It journeyed through a universe that was actively stretching, expanding every single moment of its long voyage. This is a critical, and often misunderstood, point. Let's create a more precise analogy. Imagine two explorers, you and a friend, standing on an enormous, infinitely stretchable rubber sheet. Your friend is some distance away. You both have magical boots that nail you to your specific spot on the rubber. Your friend sends a tiny, robotic ant walking towards you. The ant walks at a constant speed of 1 inch per second, times relative to the rubber surface beneath it, asterisk. But as the ant begins its journey, a powerful machine starts stretching the entire rubber sheet, doubling its size every second. The ant bravely walks on, covering its 1 inch of rubber every second. But the very rubber it is walking on is being stretched out behind it and in front of it. The destination you is constantly moving farther and farther away. The ant's journey will be much longer than it would have been on a static sheet. And by the time the ant finally reaches you, its starting point, where your friend still stands, will be a colossal distance away, much farther than the total distance the ant itself has walked. In this analogy, the ant is a photon of light, traveling at the cosmic speed limit. We are one explorer, and the galaxy that emitted the photon is the other. The stretching rubber sheet is the expanding fabric of space-time. The light from the most distant object we can possibly see was emitted about 380,000 years after the Big Bang. This light is not from a star or a galaxy. It comes from a time when the entire universe was a hot, dense, opaque fog of plasma. As the universe expanded and cooled, it reached a point where protons and electrons could finally combine to form the first neutral atoms. At this moment, the cosmos suddenly became transparent. The light that had been trapped within the plasma was set free, and it has been traveling across the cosmos ever since. Today, we detect this ancient light as a faint, uniform glow in all directions. It is called the cosmic microwave background, or the CMB. It is the oldest light in existence, the baby picture of our universe. This is the ultimate edge of our vision, the inner surface of our observable sphere. When the light from the CMB that is just now reaching our telescopes began its journey, the patch of space that emitted it was about 42 million light-years away from the patch of space that would one day become our Milky Way galaxy. For 13.8 billion years, those photons have traveled across the expanding cosmos to reach us. During that immense span of time, the very space between us and the source of that light has continued to stretch and expand. Cosmologists, using our most sophisticated models of the universe, factoring in the influence of dark matter and the accelerating expansion driven by dark energy, can calculate how much that intervening space has stretched. The result is breathtaking. That patch of space, which was a mere 42 million light-years away when it released the light we see today, is now 46.5 billion light-years away from us. It has been carried away by the expansion of space itself, just like the distant raisin in the rising bread. This gives us the true radius of the observable universe. It is not 13.8 billion light-years, it is 46.5 billion light-years. The total diameter of the sphere of reality we can, in principle, ever see is therefore a mind-numbing 93 billion light-years. Let this number sink in. 93 billion light-years. A light-year is the distance light travels in a year, nearly 6 trillion miles. Our entire Milky Way galaxy, with its hundreds of billions of stars, is about 100,000 light-years across. If you were to represent the Milky Way as the size of a single grain of sand, the observable universe would be a sphere more than 5 miles across. And within this sphere, there are an estimated 2 trillion other galaxies, each one a grain of sand, each containing hundreds of billions of suns, and likely trillions of planets. This is the scale of our cosmic fishbowl. It is the boundary of our knowledge, the limit of our sight. But this leads to the most profound question of all. What lies beyond the horizon? What is outside the observable universe? And here, we leave the realm of observation and enter the world of informed, yet breathtaking, speculation. The simplest and most widely accepted answer relies on a concept called the cosmological principle. This is the assumption that, on the largest scales, the universe is roughly the same everywhere. It is homogeneous and isotropic, meaning it has no special location and looks the same in every direction. Our cosmic neighborhood shouldn't be special. Therefore, the universe beyond our horizon is likely just more universe, more galaxies, more clusters, more cosmic web, stretching on, perhaps forever. Our 9.3 billion light-year sphere of observation is not a physical edge. It is simply our personal horizon. An alien in a galaxy 60 billion light-years away from us would have its own observable universe, its own sphere of visibility. Its sphere would include parts of the cosmos we can see, but also vast regions that are forever beyond our horizon. Likewise, we can see regions of the cosmos that are forever beyond its sight. It is like being on a ship in the middle of a vast ocean. You can see to the horizon in every direction, but you know that the ocean does not end there. A ship just beyond your horizon has its own horizon and sees a patch of ocean you cannot. The true ocean of reality is far, far larger than any single observer's view. But how much larger? This is where the theory of cosmic inflation enters the picture, and the numbers become truly beyond all human comprehension. Inflation was proposed in the 1980s by physicists like Alan Guth to solve some deep puzzles about our universe, such as why it is so remarkably flat and uniform. The theory posits that in the very first fraction of a second after the Big Bang, in a sliver of time, so small it makes a nanosecond look like an eternity, the universe underwent a period of hyper-accelerated, exponential expansion. During this inflationary epoch, a region of space smaller than a proton may have been stretched to a size larger than our entire observable universe today. It was as if the fabric of space-time itself was expanded faster than the speed of light. This does not violate Einstein's theory of relativity, which states that nothing can travel times through time-space faster than light. Inflation was the expansion times of time-space itself, which has no such speed limit. If inflation theory is correct, then the totality of the universe, the entire overarching reality, is incomprehensibly larger than the 9.3 billion light-year patch we can see. Calculations based on inflation suggest the full universe is at least 10 to the power of 23 times larger than our observable universe. This is a 1 followed by 23 zeros. It is a number so large that if our observable universe were the size of a single subatomic particle, the true universe would be larger than the observable universe is today. It is a scale so gargantuan that, for all practical purposes, the universe might as well be infinite. Our entire cosmic horizon, with its 2 trillion galaxies, would be like a single atom in the Pacific Ocean, a speck of dust in a reality without end. And the theories do not stop there. Some models of inflation, known as eternal inflation, suggest that the inflationary process may not have stopped everywhere at once. Perhaps it is still happening in other, impossibly distant regions of the cosmos. New universes, or pocket universes, could be budding off from this inflating background, each one a bubble of space-time that cools and allows galaxies to form. Our entire universe could be just one bubble in a vast, frothing sea of other universes, a multiverse of cosmic bubbles, each potentially with its own unique laws of physics, its own unique set of dimensions. This is the frontier of modern cosmology, a place where physics and philosophy merge, where the answers to our questions about size and scale lead us to contemplate the very nature of existence itself. We begin by asking how big our universe is, and we end by asking if our universe is the only one. So how can we possibly wrap our minds around this scale? Scientists often use a logarithmic map to visualize it. In the center, we place our tiny home, the Earth. Moving outwards, we cross the orbit of the Moon, then the planets of our solar system. Beyond Neptune lies the Kuiper Belt, and farther still, the vast, spherical Oort cloud, the reservoir of comets, marking the outer gravitational boundary of our Sunday. This solar system, which takes light years to cross, is just our immediate home. Far beyond it, we encounter our closest stellar neighbors in the Milky Way galaxy. Zooming out further, our entire galaxy, with its beautiful spiral arms, becomes a single object. It is just one of the larger members of the local group, a collection of a few dozen galaxies, including Andromeda, bound together by gravity. Pulling back again, our local group is revealed to be a mere suburb on the outskirts of the immense Virgo supercluster, a sprawling collection of thousands of galaxies. Even this colossal structure is just one tendril in an even grander architecture. Superclusters are woven together into unimaginably long filaments and walls of galaxies, separated by colossal voids of near-perfect emptiness. This is the cosmic web, the largest known structure in the universe, and as we pull back to the final, ultimate view, even this magnificent web dissolves into a uniform, mottled glow. We have reached the edge of our vision. We have arrived at the cosmic microwave background, the afterglow of creation, the inner surface of our 9.3 billion light-year sphere. This is the size of the observable universe. It is the portrait of everything we can ever hope to see. We began our journey with a single point of light in the night sky. We end it here, at the boundary of space-time, with a number 93 billion light-years that is both a triumphant achievement of human intellect and a humbling reminder of our cosmic insignificance. For millennia, we have strained to find our place in the cosmos. We have shifted from the center of everything to a small planet orbiting a nondescript star in a remote spiral arm of a common galaxy, in a small galactic group, lost in a supercluster within a universe so vast it may well be infinite. And yet, this same knowledge that makes us feel so small is also what makes our existence so profound. On this tiny speck of rock and water, in this forgotten corner of the cosmos, a part of the universe has woken up. Matter has become self-aware. Stardust has evolved into beings who can look back out at the vastness, wield the power of mathematics and the laws of physics, and ask the most audacious question of all: how big are you? The answer, we have found, is bigger than we ever dreamed, far bigger than we can truly comprehend. And the ultimate truth may be that the universe we can see is but an infinitesimal fraction of a reality so grand, so complex, and so utterly strange that our quest to understand it has only just begun. The night sky is not a ceiling. It is an invitation to an ocean of possibilities, stretching on, perhaps, for all of eternity. It begins where everything we know ends, not in a place but at a time. What you are seeing is the edge of vision, the very limit of light, a wall of faint shimmering energy stretched across the entire sky. This is the oldest story our telescopes can tell, an echo of a moment so violent, so total its embers still warm the cosmos. 13.8 billion years after the fact. We call it the cosmic microwave background, but a better name might be the ghost of creation. It is the baby picture of our universe, a faint, mottled glow, and we, floating in the dark, have spent a century staring back into its eyes, wondering what it all means. Now we are going to do something humanity has only ever done in theory. We are going to turn around. We are going to fall back through time. From this ancient wall of light, we begin a journey home, a journey to the beginning. Leaving the afterglow behind us, we plunge into an epoch of profound silence. A cosmic dark age. For hundreds of millions of years there were no stars to light the way, only colossal clouds of hydrogen and helium ghosts in a silent theatre. They drift, they coalesce, pulled together by a force you cannot see. Gravity, the patient, invisible sculptor. It is here in this absolute blackness that the first seeds are sown. Gravity is not just pulling matter together, it is weaving the very architecture of reality. A vast, invisible scaffolding stretches across the unlit void. The cosmic web, filaments of dark matter, the universe's hidden skeleton, forming the gravitational rivers into which all visible matter will one day flow. And as we drift through this silent, waiting kingdom, a flicker, then another, the first stars are igniting. Not like the gentle sun you know. These are monsters hundreds of times more massive. Forged from pure primordial gas, they burn a brilliant, impossible blue. Their lifespans are fleeting, a mere few million years of violent glory. They are celestial blowtorches searing the darkness. Their intense radiation rips through the neutral hydrogen fog that chokes the cosmos, an event called reionization. It is a dawning, the universe's first sunrise happening everywhere at once. Light is conquering the darkness, rendering the cosmos transparent, allowing the epic story of structure to finally become visible. As we continue our fall toward the present, the pace quickens. Those first monstrous stars die in titanic explosions. Supernovae that seed the void with heavier elements for the very first time. Carbon, oxygen, iron, the raw materials for planets, the stuff of life. These enriched clouds of gas and dust collapse under their own weight, giving birth to the next generation of stars, and not just stars but entire cities of them. The first galaxies ignite like fireflies in the immense night. Small, misshapen, chaotic collections of light and fury. They are the building blocks, the cosmic villages that will grow into empires. Gravity, the relentless shepherd, pulls them together. They collide, they merge, they dance in gravitational ballets lasting billions of years. a cosmic feeding frenzy that builds the majestic spirals and glowing ellipses. We are now billions of years into our journey. The universe is a brilliant, teeming metropolis of light. 100 billion galaxies, each with 100 billion stars. The sheer scale is an assault on the imagination. Each point of light is a sun, many with worlds of their own. And the empty spaces between them are so profound. They would take a lifetime traveling at the speed of light to cross. Let us orient ourselves in this dizzying cosmic ocean. That delicate river of light you see is our own home, the Milky Way galaxy. A spiral disk 100,000 light-years across, and we are still far, far from its center. We dive toward it, crossing the vast, dark halo that surrounds it, past ancient glittering globular clusters, stellar retirement homes. Each a dense ball of 1,000,000-old stars held in a tight gravitational grip. We breach the spiral arms, plunging into a maelstrom of creation. Here are the stellar nursery's vast nebulae of incandescent gas. Pillars of creation sculpted by the radiation of newborn suns. The universe is not static. It is alive with birth and death. We see stars in their violent youth, and we see them in their final throes. A red giant, bloated and dying, shedding its outer layers, creating a celestial jewel, a planetary nebula, its final beautiful gasp, and there the hyperdense remnant of a stellar collapse. A neutron star, a city-sized atomic nucleus spinning hundreds of times a second. A gravitational gyroscope warping the space around it. We continue inward past countless star systems, each a potential home for life, each with a story we will never know. And finally, about 2/3 of the way from the galaxy's blazing core, we find a familiar, unremarkable star, a yellow dwarf, middle-aged and stable, our sun, and orbiting it a small, pale blue dot, Earth, home. This is the destination of all that cosmic chemistry. The iron from a dying star is in your blood. The calcium in your bones, the carbon in your DNA, were all forged in the heart of a stellar crucible billions of years ago. You are in the most literal sense stardust given a voice. From the edge of the observable universe, we have returned. We have traced the unbroken chain of causality. From the first light, to the first stars, to the first life. It is the greatest story ever told, the standard model of cosmology, a triumph of human intellect and curiosity. But this entire journey, this grand cosmic narrative, hinges on one single explosive moment, the moment it all began. So now we must complete our journey. We must travel not just through space, but deeper into time, past the formation of our planet, past the birth of our sun, past the assembly of the Milky Way, past the ignition of the very first stars. We push back through the dark ages, back when the universe was a simple, foggy soup. Back further still, to when that soup was an opaque, searing plasma, a firestorm 1,000,000,000 degrees hot, too extreme for atoms to even exist. We are now just minutes into the life of the cosmos, then seconds, then microseconds. The four fundamental forces of nature, once unified, are splitting apart. The universe is expanding and cooling at a rate that defies comprehension. We are approaching the threshold, the point where our journey and our understanding must end. We are hurtling toward time zero, toward the Big Bang, and here we hit a wall far more absolute than the cosmic microwave background. Our science, our mathematics, the very laws of physics that guided us here, they shatter. They return answers of infinity, infinite temperature, infinite density, all of space and time, all the matter and energy of 100 billion galaxies, crushed into a point of zero volume, a singularity. For decades, we accepted this as the ultimate beginning. The uncaused cause, the moment of creation out of absolute nothing. It is a powerful, almost mythical idea, but it is also a deeply troubling one, because a singularity is not a physical object. It is a warning, a red flag in our equations. It is the place where our knowledge ceases to make sense. It tells us not that we have found the answer, but that our theory is incomplete. It is like reading the most epic novel ever written, only to find that the first page, the first sentence has been torn out. We are left with a story that is magnificent but rootless. a universe that springs into existence from a mathematical paradox. And this forces us to ask the most profound question imaginable, a question that until recently belonged to the realm of philosophy, not physics. What if the Big Bang was not a beginning at all? What if the singularity is a mirage, a failure of our perspective, not a failure of reality? Imagine time not as a line with a starting point, but as an eternal ocean with waves that rise and fall. What if our universe is simply the latest wave? This is the seed of a revolutionary new idea, a theory that challenges the very foundation of our cosmic story. It suggests that our universe rose from the ashes of another, a cosmos that existed before ours, a universe that grew, matured, and then collapsed. Not into a paradoxical singularity, but into a state of extreme but finite density, before rebounding, bouncing into the universe we know today. This is the theory of the Big Bounce. It reframes our creation not as a singular event from nothing, but as one moment in an eternal cycle of cosmic death and rebirth. Our Big Bang was not the first verse of the Song of Creation. It was merely the start of the next verse, in an epic that may have no beginning and no end. This isn't science fiction, it is a frontier of theoretical physics born from our deepest theories of reality. String theory, loop, quantum gravity, our boldest attempts to understand the universe. They are all pointing toward this same startling conclusion, that the beginning might have been a transition, not a creation. But if another universe did exist before ours, could we ever know? Is there any evidence, any fossil, any echo of a pre-existing cosmos? Or is its memory wiped clean by the sheer violence of the bounce? The answer astonishingly might be locked away, hidden in the minute details of that very first light we saw, in the subtle temperature fluctuations of the cosmic microwave background, in the ripples of space-time called gravitational waves, still echoing from the bounce. The ghost of creation might in fact be haunted by the ghost of the universe that came before. To find these clues, we must push our science to its absolute limits. We must journey to the quantum realm, the fabric of space-time itself, and search for the faint, delicate fingerprints of a lost cosmos. Our investigation begins now, because discovering that our universe is not the first would forever change our understanding of our place in the cosmic story. We would no longer be the inhabitants of a singular, lonely creation, but the brief, fleeting inheritors of an eternal cosmic legacy. What if time itself has a birthday, a singular explosive moment from which all of history, every star, every planet and you began to exist? For millennia, this was a question reserved for philosophers and theologians, a mystery locked away in the realm of faith. Science, it seemed, was concerned with the times, how times of the universe, not the times whence asterisk. But in the early 20th century, a revolution began to stir. Humanity for the first time started to build machines capable of eavesdropping on the cosmos tools that could capture light from the edge of creation. We were about to become cosmic detectives, piecing together a creation story grander and more bizarre than any myth ever conceived. The clues were scattered across the heavens, hidden in the faint shimmer of distant galaxies, and encoded in the very fabric of space and time. Our first task was simply to learn how to see them, to understand the language the universe was speaking. This investigation would lead us to an astonishing conclusion: our universe had a beginning. It would give us a detailed, evidence-backed history of our cosmic home, from its first fiery moments to the sprawling tapestry of galaxies we see today. Yet this very triumph of human intellect would also lead us to a terrifying wall, a point in the distant past where our laws of physics collapse into nonsense, where our story of the universe begins with a sentence that has no first word. The journey to understand what came times before times, the beginning, must start with the beginning itself. It starts with the discovery that our serene, eternal-looking night sky is a grand illusion, concealing a past of unimaginable violence and a future of relentless, accelerating change. Our first major clue, the one that shattered the static clockwork vision of the cosmos that had held for centuries, was not found in a complex equation but in a simple observation. It was a discovery made in the cold, clear air of the California mountains at the eyepiece of the world's most powerful telescope. There, astronomer Edwin Hubble was undertaking a colossal task, cataloguing the faint ghostly smudges of light, then known as spiral nebulae. He was trying to determine if they were nascent solar systems within our own Milky Way or something far more profound. By meticulously observing special pulsating stars within these nebulae, he found he could measure their distances with unprecedented accuracy. The answer that came back was staggering. These were not local clouds of gas. They were galaxies, magnificent island universes like our own, separated from us by gulfs of millions, even billions of light years. In a single stroke, the known universe expanded by a factor of infinity. But this was only half the story. As Hubble and his contemporaries analyzed the light from these distant stellar cities, they noticed something deeply strange, something consistent and unnerving. The light was stretched. The distinct spectral fingerprints of elements like hydrogen and helium, a kind of cosmic barcode, were shifted systematically towards the red end of the spectrum. This phenomenon, known as redshift, had a profound implication. Much like the pitch of a siren drops as it speeds away from you, the wavelength of light stretches or reddens as its source recedes, and the farther away a galaxy was, the more extreme its redshift, the faster it appeared to be fleeing from us. The conclusion was inescapable, and it was terrifying. Every galaxy in every direction was rushing away from every other galaxy. It wasn't that we were at the center of some cosmic explosion with everything flying away from a privileged point. Instead, the very fabric of space-time itself was expanding, carrying the galaxies along with it like raisins baked into an endlessly rising loaf of bread. This was the first pillar of our new cosmology, the expanding universe. It was a discovery that turned our understanding of reality on its head. The universe was not a static stage on which events unfolded. It was a dynamic, evolving entity, and if it was expanding now, then in the past it must have been smaller. In the distant past, smaller still, the implications of running this cosmic film in reverse were momentous. If you rewind the expansion, all those sprawling galaxies, all that empty space begins to contract. The immense voids shrink, the galactic clusters merge, and everything in the cosmos hurtles back towards a single common origin point. The entire universe, all the matter and energy we see today, must have once been compressed into a volume smaller than a grain of sand, a state of unimaginable temperature and density. From this primordial kernel, something must have happened. Something must have initiated this relentless expansion. A Belgian priest and physicist named Georges Lemaitre, years before Hubble's final confirmation, had seen this possibility in the equations of Einstein's general relativity. He called it the day without yesterday, the hypothesis of the primeval atom. We would come to know it by a more colloquial and far more famous name, the Big Bang. It was a theory so outlandish, so contrary to all human experience, that it was met with deep skepticism. A universe born from a single point. It sounded more like a creation myth than a scientific hypothesis. For a theory to survive, it needs more than elegant logic. It needs to make predictions, testable claims about the nature of reality that can be verified or falsified. If the early universe was truly this incredibly hot, dense furnace, then the after effects of that inferno should still be detectable today. It was a young physicist named George Gamow, along with his students, who in the 1,940 seconds reasoned through the consequences. They imagined this primordial soup a state so hot that atoms could not form. Electrons, protons and neutrons would have been unbound, swimming in a blindingly bright fog of high-energy photons, particles of light. In this state, the universe was completely opaque. Light could not travel far before crashing into a charged particle being absorbed and re-emitted in a chaotic cosmic pinball machine. But as the universe expanded, it also cooled. Gamow predicted that after a few 100,000 years, it would have cooled enough for protons and electrons to finally bind together, forming the first stable neutral hydrogen atoms. This moment, which we now call recombination, would have been a transformative event. Suddenly, with the charged particles locked away inside atoms, the photons were free. The universe in an instant became transparent. That primordial light, a brilliant flash from the dawn of time, would have been released in all directions, free to travel across the cosmos, unimpeded for all of eternity. Gamow and his team calculated that this ancient light, though initially searingly hot, would have been stretched by the subsequent 13.8 billion years of cosmic expansion. Its wavelength would have been shifted all the way from visible light past infrared into the microwave portion of the spectrum. It would be incredibly faint, a whisper of creation, a background temperature just a few degrees above absolute zero, coming from every single point in the sky with no discernible source. This prediction, the existence of a cosmic microwave background radiation, or CMB, became the smoking gun of the Big Bang. For nearly 2 decades, this predicted echo of creation remained a theoretical ghost. No one had the equipment sensitive enough to detect it. Then in 1964, at Bell Labs in New Jersey, 2 radio astronomers, Arno Penzias and Robert Wilson, were struggling with a problem. They were using a large, horn-shaped antenna to study microwave signals from the Milky Way, but they were plagued by a persistent, annoying hiss. It was a faint, uniform noise that they simply could not eliminate. They checked their equipment, rewired their systems, and even famously cleaned out pigeon droppings from the antenna, suspecting it might be the source of thermal interference. But the hiss remained. It was everywhere. No matter where they pointed their antenna in the sky, day or night, season after season, the same faint, inexplicable microwave signal was present. They were completely by accident listening to the oldest sound in the universe. Unbeknownst to them, just a few miles away at Princeton University, a team of physicists was building a detector specifically designed to find the very signal Penzias and Wilson were trying to eliminate. When the 2 groups finally connected, the truth dawned. The hiss was not an error. It was the fossil light from the Big Bang. It was the baby picture of our universe, the embers of that initial cosmic firestorm, cooled and stretched over eons, finally washing over the Earth. This discovery, the second great pillar of the theory, transformed the Big Bang from a curious hypothesis into the ruling paradigm of modern cosmology. We were no longer just inferring the past. We were directly observing the afterglow of creation. The evidence was compelling, but the theory held yet another, even more precise prediction. If the conditions in the first few moments after the Big Bang were as hot and dense as the model suggested, then the universe itself would have acted as a colossal thermonuclear reactor. The first 3 minutes of existence were a period of such extreme temperature and pressure that the fundamental particles forged in the initial moment, protons and neutrons, began to fuse together. This wasn't the slow, steady fusion that powers stars, but a frantic, universe-spanning burst of creation known as Big Bang nucleosynthesis. It was a fleeting epoch. The universe was expanding and cooling so rapidly that this cosmic furnace was only active for a matter of minutes. In that short window before the cosmos became too cool and diffuse for fusion to continue, a specific predictable ratio of the lightest elements should have been cooked into existence. The theory made a stark prediction: for every 10 hydrogen nuclei, there should be roughly 1 nucleus of helium, along with tiny trace amounts of lithium and other light isotopes. The vast majority of the primordial matter should remain as simple hydrogen. Anything heavier, the carbon in your body, the oxygen you breathe, the iron in your blood, would have to be forged much later in the hearts of dying stars. This provided a third powerful test. We could aim our telescopes at the most ancient, pristine objects we can find, the oldest stars, the most distant gas clouds that have been largely untouched by later stellar processing, and measure their chemical composition. We could analyze their light and see if this primordial recipe, this elemental fingerprint from the first 3 minutes, was actually there. And when we looked, the results were breathtaking. Across the cosmos, in the atmospheres of the most ancient stars, and the spectral lines of the most remote quasars, we found it. The universe in its infancy was indeed composed of roughly 75% hydrogen and 25% helium, with the predicted trace elements in near perfect accord with the calculations. This was not a vague qualitative match. It was a stunningly precise quantitative victory. The theory didn't just say times that times these elements should exist. It predicted their proportions with incredible accuracy. This third pillar cemented the foundation of the Big Bang model. We now had 3 independent, powerful lines of evidence, all pointing to the same inescapable narrative. First, the observed expansion of the universe, which when reversed points to a beginning. Second, the discovery of the cosmic microwave background, the literal afterglow of that hot, dense beginning. And third, the observed abundance of light elements, the precise chemical residue cooked in that primordial furnace. Together, they tell a triumphant and coherent story of cosmic evolution. We can now trace our history from the first microsecond through the formation of atoms, the birth of the first stars and galaxies, the creation of heavy elements, the formation of our solar system, and ultimately to this very moment as you ponder your place within this grand cosmic saga. It is one of the greatest intellectual achievements in human history, a testament to our relentless curiosity. We have a story of the universe that works, but it is a story with a missing first page. For all its power and predictive success, the Big Bang Theory suffers from a profound and fundamental limitation. As we rewind the cosmic clock, pushing the equations of general relativity further and further back in time, the universe gets hotter, denser, and smaller. At the very beginning, at time zero, our mathematics break. The equations predict a point of infinite density, infinite temperature, and zero volume, a place where all the matter and energy of the observable universe is crushed into a geometric point with no dimensions. This is the gravitational singularity. It is a concept that defies all logic and physical intuition. It's not just that we don't know what it was like, it's that the very laws of physics as we understand them cease to have any meaning. Space-time curvature becomes infinite. Cause and effect, the very bedrock of scientific inquiry, dissolve. Our theory, the one that so beautifully describes the evolution of the universe from a fraction of a second times after times its birth, provides no information whatsoever about the moment of birth itself or what might have existed before it. The singularity is not a physical prediction. It is an admission of ignorance. It is the mathematical equivalent of a "here be dragon" sign on the map of reality. It tells us that our current theories, general relativity, and the standard model of particle physics are incomplete. They are like a magnificent cathedral built on the edge of a bottomless cliff. This is the great unanswered question that haunts modern cosmology. The Big Bang Theory does not describe the origin of the universe. It describes the aftermath of an origin we do not understand. It tells us what happened times after times the bang, but it cannot tell us what banged, why it banged, or what was happening a moment before it banged. Did the universe truly spring into existence from absolute nothingness? A violation of every physical principle we hold dear? Was there a before? And if so, what form did it take? The singularity presents a veil through which we cannot see, a cosmic firewall that separates us from any knowledge of a prior state. It is here at this wall of infinity that our triumphant story of the cosmos grinds to a halt, leaving us with the deepest mystery of all. To breach this wall, to even begin to ask what came before the beginning, we must look beyond the Big Bang itself. We need a new kind of physics, a new vision of the cosmos, one that can tame the infinities, and perhaps reveal that our universe's beginning was not a true beginning at all, but merely one event in a much grander and possibly eternal cosmic cycle. And so we have it, a triumphant narrative of cosmic creation etched into the fabric of space-time itself. A story that begins in an unimaginable flash of light and heat, expanding outward for nearly 14 billion years to give us the galaxies, the stars, the planets, and ultimately ourselves. It is by every measure one of humanity's greatest intellectual achievements. For a century, this story, our story of the Big Bang, has been the bedrock of modern cosmology. It is elegant, it is powerful, and its predictions have been confirmed with astonishing precision, from the whisper of the cosmic microwave background to the precise abundances of the lightest elements forged in that primordial fire. It's a story that feels almost complete. Almost. Because if you look closely at that first foundational chapter, at that single brilliant point from which everything is said to have emerged, you find a crack. It's a subtle fracture at first, a detail you might overlook in the grandeur of the epic, but as you trace its edges, you realize it is not a small imperfection. It is a gaping chasm, a place where our story doesn't just stumble, it utterly collapses. This is the uncomfortable secret residing at the very heart of our creation myth, a ghost in the machine of modern physics. It's a point in time, or rather a point times before times, time known by a simple yet terrifying name, the singularity. To understand the crisis it represents, you must retrace our steps, journey back with us, not just through the eons of galactic evolution, but past the birth of the first stars before the universe was even transparent to light. We push backward through time, and as we do, the universe, we know, inverts. our vast, cold and dark cosmos contracts. Galaxies, once rushing away from each other, now fly back together in a great cosmic reunion. The space between them vanishes. The temperature, once hovering just a few degrees above absolute zero, begins to skyrocket, first to thousands, then millions, then billions of degrees. We are compressing all the matter and all the energy of 100 billion galaxies into a volume that gets smaller and smaller. First the size of our solar system, then the size of a star, then the size of the Earth, then the size of a marble. Our guide on this impossible journey is Einstein's theory of general relativity. It is the master equation of the cosmos, a flawless map that describes how gravity shapes the universe on the largest of scales. And for this entire journey backward, it has served us perfectly. But as we approach that initial moment, as the entire observable universe is crushed into a space smaller than a single atom, Einstein's beautiful equations begin to scream. The numbers they produce, the ones that describe the density of matter and the curvature of space-time, spiral out of control. They surge past any comprehensible physical quantity and race towards a value that has no place in the physical world. They race towards infinity. This is the singularity, not a place but a boundary, a mathematical wall our theories crash into. It is a point of infinite density, infinite temperature, and infinite curvature, a state of existence so extreme that the very concepts of space and time as we understand them dissolve into meaninglessness. It is in the bluntest terms the point where physics breaks down. Our most trusted guide, general relativity, the theory that predicted black holes and gravitational waves, the theory that maps the grand dance of galaxies, simply gives up. It holds up its hands and tells us that it cannot go any further. It cannot tell us what the singularity times is, times, or what came before it. For general relativity, this is not the beginning of the universe. It is the end of the explanation. For decades, this was a problem cosmologists were willing to live with. The singularity was seen as an unavoidable feature of the model, a placeholder for a future more complete theory. Perhaps they reasoned the question of before was nonsensical, like asking what is north of the North Pole. The Big Bang singularity in this view was the true genesis, an absolute beginning where time itself was born. But over time, this view began to feel less like a profound physical truth and more like a statement of surrender. A quiet but persistent disquiet began to spread through the community. Is it really satisfying to say that our entire universe, with all its intricate laws and majestic structures, erupted from a state of infinite chaos that defies those very laws? Did everything truly emerge from a point of mathematical K-mate? Nonsense. This isn't just a philosophical preference for a tidy origin story. The singularity presents a fundamental paradox. The universe today is governed by exquisite and precise physical laws of quantum mechanics, thermodynamics, and relativity. These principles are what allow for the orderly formation of atoms, stars, and life itself. The standard Big Bang model asks us to accept that all of this intricate lawful machinery was born from its own complete and utter negation. It suggests that the ultimate source of all cosmic order is a state of absolute lawless disorder. It's like discovering that a perfectly engineered Swiss watch was spontaneously assembled in the heart of a nuclear explosion. It feels deeply intuitively wrong. The growing unease solidified into a clear mandate. The singularity must be a sign that our theory is incomplete. It is not a description of a real physical event. Instead, it is a desperate flare sent up by general relativity, a warning that we have pushed the theory beyond its jurisdiction into a realm where it no longer applies. Einstein's masterpiece, you see, is a theory of the very large. It describes gravity as the graceful curvature of space-time, a smooth, continuous fabric. It works beautifully for planets, stars, and galaxies. But the origin of our universe was an event of the very small. The entire cosmos was once smaller than any subatomic particle you can imagine. And in that microscopic kingdom, a different set of rules holds sway. Here, in the realm of the quantum reality, behaves in ways that defy all classical intuition. It is a world of probabilities, not certainties. A place where particles can be in multiple places at once, where energy is not smooth and continuous, but comes in discrete packets or quanta. This is the world described by quantum mechanics, the other great pillar of 20th century physics. And for 100 years, these two pillars, general relativity and quantum mechanics, have stood apart. They are like two magnificent languages that describe the same world, but which are mutually incomprehensible. General relativity gives us the flowing poetry of the cosmos. Quantum mechanics gives us the staccato probabilistic grammar of the particle. And they have never been successfully translated into one another. This is the great unresolved conflict in modern physics. We have a near-perfect theory for gravity and the large-scale universe, and a near-perfect theory for the other forces of nature at the smallest scales. But we have no single coherent framework that can describe events where the very large is also the very small. We lack a theory for phenomena that are simultaneously infinitesimally tiny and unimaginably massive and energetic. And there are two places in the universe where such a theory is not a luxury, but an absolute necessity, at the heart of a black hole and at the beginning of our universe. Both are places where general relativity predicts a singularity, a point of infinite density. And both are places where we know that prediction must be wrong, because in a region that small, the bizarre rules of quantum mechanics must take over. The quest to unite these two theories, to weave them into a single, deeper understanding of reality, is the holy grail of theoretical physics. It is the search for a theory of quantum gravity. Such a theory would provide the missing grammar, a way to describe how the fabric of space-time itself behaves at the quantum level. It would replace Einstein's smooth, continuous sheet of space-time with something more fundamental. Perhaps a fabric woven from discrete quantum threads, or a shimmering foam of probabilistic geometries. We don't yet know the final form this theory will take. Physicists are exploring multiple paths with names like string theory and loop quantum gravity, each a bold and brilliant attempt to write the first sentence of the cosmic story in a language that doesn't break down into infinities. But across these different approaches, a stunning and revolutionary idea begins to emerge, a common theme that echoes through the complex mathematics. If you build a theory of quantum gravity, if you successfully apply the principles of the quantum world to the birth of the universe, the singularity vanishes. It is smoothed out, resolved by the new, deeper physics. In a quantum universe, you can't actually crush an infinite amount of energy into an infinitely small point. The quantum world itself resists. A fundamental tenet of quantum mechanics, the uncertainty principle, suggests there is a limit to how small and how energetic you can make something. It places a quantum floor on reality, a minimum possible size. So, as we rewind time in this new picture, guided not just by Einstein, but by a future theory of quantum gravity, our journey backward is different. The universe still contracts the temperature, and density still rise to unimaginable levels far beyond anything we can create in our most powerful particle accelerators. But it does not spiral into infinity. As the cosmos shrinks down to its minimum possible quantum size, a new force, a quantum pressure, begins to push back. It's a repulsive aspect of gravity itself, a feature invisible in Einstein's theory but dominant at these extreme scales. This quantum pressure fights against the relentless crush of collapse, becoming stronger and stronger as the universe gets smaller. Finally, at the moment where the old theory predicted a catastrophic singularity, something else happens. The collapse halts. For an infinitesimal fraction of a second, the universe, compressed into a quantum seed of pure energy, holds its breath. The immense inward pressure of gravitational collapse is met by an equally immense outward pressure from the new quantum gravity. And then this new physics does not just stop the collapse, it reverses it. The ultimate compression gives way to a new spectacular expansion. The cosmic seed, having reached its maximum density, recoils. It doesn't break. It doesn't begin from an impossible infinity. It bounces. This single, elegant idea changes everything. The Big Bang is no longer a moment of absolute creation from nothing, born from a physically impossible singularity. Instead, it becomes the Big Bounce, a moment of transition, a pivot point in a story that may be far, far older than we ever imagined. It replaces the problematic law-breaking singularity with a comprehensible physical event governed by the laws of quantum gravity. Our universe didn't begin with a bang. It was reborn from the ashes of a previous phase of existence. The violent expansion we see as our cosmic origin was in this radical new telling the result of a stupendous rebound from a prior contracting cosmic epoch. Suddenly, the question that was forbidden, the question of what came before the Big Bang, is no longer meaningless. It becomes the central question. If our universe is the result of a bounce, what was it? Bouncing times from times. What did that predecessor universe look like? Was it a universe like our own, full of stars and galaxies that had lived out its life and was now collapsing back in on itself? Or was it something far stranger, an alien, geometry of which our own cosmos is but a faint echo? The blank page at the beginning of our story is suddenly filled with the tantalizing possibility of an entire prequel. A lost cosmic history that took place on the other side of the bounce. We are standing at a profound fork in the road of our understanding. Down one path lies the traditional story, a universe born from an inexplicable, lawless singularity, an ultimate beginning beyond which we cannot and should not look. It is a story of a singular creation event. Down the other, more speculative yet more physically consistent path lies the story of the bounce. A universe with no true beginning and perhaps no true end. A universe that may be one link in an eternal chain of cosmic cycles, contracting into a quantum furnace and rebounding into a new expansion over and over again. This isn't just a technical debate for cosmologists in ivory towers. This is a fundamental challenge to our conception of time, existence, and our place within it all. It asks us to consider that the 8 billion years we can see might just be the latest chapter in a book whose full length we have not yet dared to comprehend. Did our universe truly spring into being from a point of impossible physics? Or is its birth a far more graceful, far more ancient, and far more mysterious story? A story not of a singular bang, but of an eternal echo. The clues to answering this question are hidden not in the future, but in the deepest structures of the past, waiting for us to find them. And so we find ourselves staring into the abyss, brought to the very edge of existence by our own logic. We followed the universe backward through the great cosmic diaspora of galaxies, past the birth of the first stars and into the searing plasma of its infancy. Our guide, general relativity, the masterpiece of a generation, led us faithfully. But here at the threshold of the beginning, it abandons us, pointing to a single impossible point of infinite density, infinite heat, infinite absurdity, a singularity, a place where the laws of physics, the very language we use to describe reality, dissolve into nonsense. This is the wall at the end of science, a full stop written into the fabric of space-time. Or is it, what if this wall is not an endpoint but a mirage? What if the singularity, this monster of the infinite that has haunted cosmology for a century, is simply a symptom of a deeper, more elegant truth we have yet to embrace? What if the beginning was not a beginning at all, but merely a turning of the page? To find the answer, we must dare to imagine the unimaginable. We must rewind the clock even further, past the initial moment of the Big Bang, into a realm that standard cosmology declares off-limits. We must envision a universe not born from nothing, but reborn from something. This radical, breathtaking idea has a name that echoes its very nature, the Big Bounce. It proposes that our Big Bang was not a singular creation event, but the spectacular rebound from the collapse of a previous ancient cosmos. Imagine it not as an explosion, but as the reversal of an implosion, the ultimate cosmic reset, a universe that does not just die but breathes, inhaling for trillions of years into a great collapse, a big crunch, before exhaling again in the fiery burst of a new Big Bang, our Big Bang. It is a cyclical, eternal story, one that replaces the terrifying enigma of the singularity with the sublime rhythm of cosmic renewal. This is not just a philosophical preference, it is a theory forged in the crucible, where our two greatest descriptions of reality, relativity, and quantum mechanics are forced to reconcile. To understand the bounce, we must first journey into that prior universe, into its final moments. Picture a cosmos unimaginably older than our own. Its stars have all burned out their light, extinguished like a trillion dying embers. The galaxies, once majestic glittering islands, have bled their structure away, their remaining black holes and cold cinders drawn together by the relentless patient pull of gravity. For eons, the expansion that once defined it has slowed, halted, and finally reversed. A great homecoming has begun. Distant clusters of matter which had spent trillions of years fleeing from one another now begin a slow, inexorable fall back towards a common center. It is the story of our universe told in reverse. Gravity, once the gentle sculptor of galaxies, becomes the unyielding warden pulling everything inward. The universe is contracting. Space itself is shrinking, pulling the cold, dark remnants of stars and planets into an ever denser, ever hotter cosmic maelstrom. As this big crunch accelerates, the cosmos transforms into a crucible of unimaginable violence. The background temperature, once near absolute zero, begins to climb. First to hundreds, then thousands, then millions of degrees. The dead cores of stars, the cold neutron stars and white dwarfs, are heated until they vaporize into a uniform gas of elementary particles. Black holes, the gravitational champions of the old universe, find themselves in a contracting space and begin to merge at a terrifying rate, creating a gravitational crescendo that shakes the very fabric of space-time. The universe becomes a pressure cooker the size of reality itself, a gravitational fever dream where everything is crushed together. According to the mathematics of general relativity alone, this process has only one destination: that dreaded singularity. Everything crushed to an infinitely small point. Annihilation, the end of the story. But it is precisely here, in this moment of ultimate compression, on a scale so small it defies imagination, that a new law of physics awakens. This is the Planck scale, a fundamental graininess to reality 100 million trillion times smaller than a single proton. Down here, the smooth geometric elegance of Einstein's space-time gives way to the frenetic, uncertain world of quantum mechanics. And in that world, the concept of infinity finds no home. Here, the universe reveals a hidden strength, a final defense mechanism against total collapse. This defense is born from the very nature of space-time itself. Think of space-time not as a passive stage, but as an active physical entity. You can bend it, warp it, stretch it, but according to the principles of quantum gravity, you cannot shrink it to nothing. Just as a particle cannot be pinpointed to an exact location and have a definite momentum, space-time itself has a fundamental, irreducible minimum volume. There is a quantum rigidity to the fabric of reality. When the collapsing universe tries to compress beyond this ultimate limit, a new force emerges, a force of repulsion born from the quantum foam of space-time itself. It's as if the very weave of reality pushes back, refusing to be torn asunder. This quantum pressure, a phenomenon with no classical equivalent, grows exponentially as the universe shrinks, becoming for a fleeting instant the most powerful force in existence. It overwhelms even the infinite-seeming pull of gravity that has gathered the entire mass of a previous cosmos into a single hyper-dense furnace. This is not a collision of matter in the way we understand it. It is a confrontation with the fundamental nature of space and time. The unstoppable force of gravitational collapse meets the immovable object of quantum reality, and reality wins. The inward rush of all that energy and matter having reached the point of maximum density, a density that is staggering beyond all comprehension, but crucially, time's finite times is halted. For an infinitesimal moment shorter than any clock could ever measure, the universe holds its breath, and then it bounces. The colossal energy of the collapse, now reversed by quantum pressure, becomes the explosive engine of a new expansion. This is our Big Bang. Not a magical creation from a point of nothingness, but a violent physical rebound. The temperature and density are at their peak, a state we call the Planck epoch, and from this cauldron of pure, seething energy, the universe we know begins to expand and cool. The fundamental particles precipitate from the energy field. The laws of physics as we know them crystallize from the cooling plasma. The great cosmic story we have pieced together from the first 3 minutes to the formation of Earth unfolds exactly as our observations tell us it did. But its origin story has been profoundly rewritten. The Big Bounce does not replace the Big Bang. It gives it a prequel. It provides the mechanism, the physical process that ignited the cosmic fire, saving physics from the paradoxical flames of the singularity. this elegant solution does more than just solve the problem of the infinite. It ripples outward, offering potential answers to some of the most profound and persistent mysteries in cosmology. Consider the so-called flatness problem. Our universe appears to be against all odds perfectly geometrically flat. Any significant curvature, positive or negative, in the early universe would have been magnified over 13.8 billion years of expansion, causing it to either collapse back on itself long ago or fly apart so quickly that no structures could form. The standard Big Bang model has to assume this flatness was an initial condition of exquisite, almost impossible perfection. But in a big bounce scenario, this flatness could be a natural outcome. The long, slow period of contraction in the previous universe would have had eons to iron out any large-scale wrinkles or curves, smoothing space-time to an incredible degree. Then the bounce itself would preserve that flatness, launching the new universe on its perfect trajectory. It's like stretching a crumpled sheet of fabric over a vast drum, pulling it taut for ages until every crease vanishes, and then striking it to begin the vibrations anew. Then there is the horizon problem, another deep puzzle for the standard model. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it is astonishingly uniform in temperature in every direction we look. Regions of the sky that are now billions of light years apart, and which, according to the standard Big Bang, could never have been in causal contact, somehow share the same thermal properties. It's like finding two people on opposite sides of the Earth who have never met or communicated, yet have their body temperatures synchronized to 1,000th of a degree. The standard model solves this with a theory called cosmic inflation, a period of hyper-accelerated expansion just after the Big Bang. But the Big Bounce offers a more intuitive, less exotic solution. In the vast eons of the contracting phase of the previous universe, all these now distant regions were once close together. They had more than enough time to exchange energy and information to mix and settle into a state of near-perfect thermal equilibrium, like steam filling a room. The bounce then simply magnified this pre-existing uniformity onto the grand canvas of our expanding cosmos. The smoothness of our universe isn't a miracle of the first second. It is an inheritance, a relic from a past life. By replacing a beginning with a transition, the Big Bounce transforms our entire perception of our cosmic home. It suggests that the universe has a history far grander and more ancient than we ever dared to imagine. Our 13.8 billion-year-old cosmos may be just the latest chapter in an epic that has no beginning and perhaps no end. The matter that makes up your body, the iron in your blood and the calcium in your bones, may not have been forged in the Big Bang, but could be the recycled remnants of stars and galaxies from a universe that existed before our own. We could be living quite literally among the ghosts of a fallen cosmos, resurrected in the crucible of the bounce. This idea elevates the universe from a singular event to an eternal self-perpetuating system. It introduces a grand cyclical narrative that resonates with ancient philosophies, the idea of the cosmic wheel of creation and destruction, of Brahma's breath-inhaling and exhaling worlds. Except now, this mythic-sounding story is written in the precise, demanding language of theoretical physics and quantum gravity. It paints a picture of a cosmos that is not just expanding but is alive, with a kind of quantum heartbeat, a rhythm of collapse and rebirth playing out over timescales that dwarf human comprehension. Each bounce could potentially reset the cosmic clock, creating a new universe with its own unique story, yet carrying the indelible imprints of its predecessor. It is a vision of profound conservation where nothing is ever truly lost, merely reformed. The end of one universe is not an apocalypse but a metamorphosis, the closing of one cosmic breath before the exhalation of the next. This shifts our entire emotional and philosophical grounding. We are no longer the inhabitants of a universe that exploded out of an inexplicable singularity and is now coasting towards an eventual cold, dark death. Instead, we may be participants in a single phase of a magnificent, undying cycle. Our existence is not the product of a one-time fluke, but a natural repeating outcome of the fundamental laws of reality. But this grand, beautiful theory, for all its power to resolve our deepest paradoxes, also presents us with a new, tantalizing set of questions. If there was a universe before ours, what was it like? Was it a near-perfect mirror image of our own, or was it wildly different, governed by subtly altered physical constants? Is there any way we could ever know? Can we find evidence is this prior existence a cosmic fossil embedded in the fabric to our own reality? Could there be faint scars from the violence of the bounce, or subtle echoes of a pre-existing structure? Still lingering in the faint glow of the microwave background, or in the intricate web of galactic clusters, the Big Bounce, in solving the mystery of the beginning, has opened the door to an even more profound inquiry, the search for our own cosmic ancestry. We have moved from asking how times our universe began to asking what came times before, asterisk. The quest now is to find a message in a bottle, a whisper from across the chasm of the bounce, a sign that we are not the first. So we stand at the precipice of an idea so profound it threatens to shatter our very definition of a beginning. If the universe we know is not the first but merely the latest in a chain of cosmic reincarnations, then the questions that arise are as vast and dizzying as the cycles themselves. What would it mean to live in the aftermath of a former creation? What ghosts of that previous existence might still haunt our own cosmos, hiding in the quantum shadows, or written into the very fabric of physical law? To even begin to answer this, we must first confront the nature of the transition itself, the monumental, universe-crushing, universe-birthing event of the bounce. This is not simply a reset button, it is a violent passage through a gravitational crucible of unimaginable intensity. Imagine for a moment that prior cosmos, it could have been a near-perfect twin of our own, expanding for trillions of years, its galaxies glittering with stars, its planets perhaps even teeming with forms of life we can scarcely conceive. It would have followed its own grand narrative, a story of stellar birth and death, of galactic collisions, and the slow, inexorable march of entropy. But its fate was sealed. Its expansion would have eventually slowed, halted by the collective gravitational pull of everything it contained, and begun the long, terrible fall inward. This was not a collapse of a single star, but of everything. Space itself, the very stage of existence, would have been contracting, pulling all matter and energy into a tightening knot. As this predecessor universe hurtled toward its end, it would have become a place of pure chaos. Galaxies, once separated by impassable voids, would have merged into a single incandescent supercluster. Stars would have been torn apart, their constituent atoms stripped bare by tidal forces and searing radiation. The universe would have transformed into a superheated plasma, a cosmic inferno, where the laws of physics as we know them begin to buckle and strain under the pressure. The final moments would be a plunge into a state of such extreme density and energy that our current theories rooted in general relativity simply break down. This is the singularity, the point of infinite density that the Big Bang model starts with, and which the Big Bounce must somehow avoid. But what if that previous universe wasn't a mirror of ours at all? The cyclical model opens the door to a far more radical possibility that the fundamental constants of nature, the very rules of the game, could be different in each iteration. Perhaps in the universe before ours, gravity was 100 times stronger, preventing the formation of large, stable galaxies and leading to a cosmos of short-lived, monstrously massive stars that quickly collapsed into black holes. Or maybe the electromagnetic force was weaker, meaning atoms could not hold together, resulting in a cold, formless universe of diffuse gas that never ignited into stars at all. Each bounce could be a cosmic reshuffling of the deck, a chance to deal a new hand of physical laws. This concept presents a tantalizing if unsettling solution to one of cosmology's deepest mysteries, the fine-tuning problem. We find ourselves in a universe where the physical constants appear exquisitely calibrated to permit the existence of complexity, chemistry, and ultimately life. If the strength of the nuclear force were altered by a mere fraction of a percent, stars would either burn out too quickly or never ignite in the first place. If the mass of the electron was slightly different, complex molecules would be impossible. The Big Bang model offers no explanation for this apparent miracle. It simply accepts these values as given a set of initial conditions that just happen to be right. A cyclical universe, however, reframes the question entirely. It suggests that we don't live in a uniquely special universe, but in one of a potentially infinite sequence of universes. Many, perhaps most of these cosmic cycles would have been sterile and barren, their physical laws inhospitable to any form of structure. They would have been born, expanded, and collapsed back into the bounce, their stories playing out on an empty stage. Our universe, with its life-giving properties, is then not a miracle but a statistical inevitability. We exist here and now because this is one of the cycles where the conditions times were times right. We have, in a sense, won a cosmic lottery played out over eons, our existence made possible by a long chain of failed, lifeless universes that came before. The bounce in this view acts as a great cosmic filter, a mechanism for exploring every possible physical reality until it stumbles upon one like ours, capable of producing observers to wonder at its own existence. Yet for this grand vision to hold, we must ask a critical question. Could any information, any relic, or memory of that previous cosmos survive the bounce? The journey through that ultra-dense, ultra-hot state would be the most destructive process imaginable. It would seem to be the ultimate eraser, a universal amnesia machine that wipes the slate clean. The very atoms that might have made up a planet, a star, or a living being in a prior cycle would be annihilated, their substance dissolved back into a quark-gluon plasma, a fundamental soup of particles. Any structure, any pattern from the grandest supercluster of galaxies down to the most intricate molecule would be utterly obliterated. But perhaps not everything is lost. Some theorists speculate that the most fundamental entities of all might carry a faint echo across the divide. Gravitational waves, for instance, are ripples in the fabric of space-time itself. Unlike light or matter, they are incredibly difficult to stop or absorb. Could it be that the violent death throes of the last universe, the final cataclysmic merger of all its black holes, sent out gravitational shockwaves so powerful that they could somehow perturb the quantum state of the newly forming cosmos? If so, we might be able to search for their ghostly signature, a faint anomalous pattern imprinted on the cosmic microwave background radiation, the afterglow of our own Big Bang. It would be the universe's oldest scar, a birthmark from a previous life. Another tantalizing possibility lies within the enigmatic nature of black holes. In our current understanding, what falls into a black hole is lost forever, hidden behind an event horizon, but in some models of quantum gravity, information is never truly destroyed. Could it be that the supermassive black holes that dominated the final moments of the contracting universe acted as cosmic archives, as they were squeezed together in the final crunch? Perhaps their immense gravitational fields could have somehow imprinted their stored information onto the nascent universe during the bounce. This is highly speculative, bordering on science fiction, but it pushes us to reconsider the very nature of information and its persistence in the face of cosmic annihilation. We would not be looking for the ruins of a former civilization, but for a subtle statistical anomaly in the distribution of galaxies, a faint mathematical preference in the laws of physics, the ghost of a prior order whispering from beyond the veil of our own beginning. However, as we allow our imaginations to wander through these breathtaking landscapes of possibility, we are violently pulled back to reality by a formidable scientific roadblock, a problem so fundamental it has been called the greatest challenge to any cyclical model of the universe. This is the implacable tyranny of the second law of thermodynamics. You see it every day. A hot cup of coffee cools down, never spontaneously heating up. A shattered glass does not reassemble itself. In any closed system, entropy, a measure of disorder, randomness, and useless energy, can only increase. It is the universe's one-way street, the unwavering arrow of time that points from order to decay. Our universe began in a state of remarkably low entropy, a highly ordered condition that has allowed for the formation of complex structures like stars and galaxies. Over the last 13.8 billion years, entropy has been steadily increasing as stars burn their fuel and radiate it away as disordered heat. The ultimate fate of our universe, if it expands forever, is a state of maximum entropy known as heat death, a cold, dark, and featureless void where nothing interesting can ever happen again. Now apply this inexorable law to a cyclical universe. If our universe was born from the collapse of a previous one, That previous universe must have had an even lower entropy state at its beginning than ours did, and the one before that lower still. If you trace this cycle backward in time, you are forced into an absurdity, an infinite chain of universes, each beginning with a more and more exquisitely ordered state, approaching a state of perfect, impossible order at the beginning of time. This completely contradicts the idea that a cyclical model avoids the problem of a beginning. It simply pushes the problem of an unnatural initial state infinitely far into the past. Conversely, if we look forward, the problem is just as dire. With each cycle of expansion and contraction, the total entropy of the universe should increase. Each bounce would be messier and more disordered than the last. Black holes would form and merge, generating enormous amounts of entropy. Radiation would be produced and thermalized. With every cycle, the universe would get hotter, larger, and more chaotic. After just a few bounces, it would likely grow so large and disordered on its rebound that it would never have enough gravity to halt its expansion and collapse again. The cycle would be broken, leading to a final, eternal expansion into heat death. An infinite chain of bounces seems thermodynamically impossible. The universe, it seems, should have died of old age eons ago. How can the Big Bounce theory possibly overcome this? How can it reverse the sacred arrow of time? Scientists working on these models have proposed several radical mind-bending solutions. One idea is that the bounce itself is a kind of entropy reset mechanism. Perhaps the extreme physics at play during the turnaround can somehow rejuvenate the universe, squeezing out the disorder and creating a new low-entropy state from the ashes of the old. This would require new physics, a mechanism that can violate the second law of thermodynamics on a cosmic scale, even if only for a fleeting moment in the crucible of the bounce. This is a profound challenge, as it means rewriting one of the most well-tested and fundamental principles in all of science. Another, even more startling proposal suggests that the universe doesn't reset entropy, but instead reverses the arrow of time itself. In this scenario, championed by physicists like Julian Barber and Sean Carroll, the bounce represents a point of temporal symmetry. Imagine time flowing away from the bounce in two opposite directions. On our side of the bounce, time flows forward and entropy increases as our universe expands. But on the other times, side in the contracting pre-universe time would flow in the opposite direction from our perspective. An observer in that contracting universe would experience their own future as a collapse, yet for them entropy would also be increasing in their forward direction of time. The Big Bounce would be a common past for two universes each, expanding and growing more disordered as they move away from the central moment of creation. It is an elegant but deeply strange idea, suggesting our past is another universe's future, and that the river of time flows in two directions from a single timeless source. Beyond the monumental hurdle of entropy, there remains the question of the bounce mechanism itself. What physical force could possibly be strong enough to halt the gravitational collapse of an entire universe and reverse it? General relativity, Einstein's theory of gravity, offers no escape. In its equations, a contracting universe inevitably leads to a singularity, a point of infinite density where the theory itself ceases to make sense. If a bounce is to happen, we need a new theory, a deeper understanding of gravity that takes over in these extreme regimes. This is where the frontier of theoretical physics, specifically loop quantum gravity, offers a potential lifeline. As we explored earlier, this theory reimagines space-time not as a smooth, continuous fabric, but as a discrete granular structure woven from indivisible loops or atoms of space-time at the Planck scale. In this picture, there is a fundamental limit to how much you can compress space. You can't squeeze it to an infinitely small point because you eventually run into these indivisible quantum units. This creates a powerful repulsive force, a kind of quantum pressure that pushes back against the crush of gravity. As the contracting universe gets squeezed down toward the Planck density, this quantum pressure would build to an incredible degree. It would become the most powerful force in the cosmos, strong enough to finally overpower gravity, halt the collapse, and literally bounce the universe back into a new phase of expansion. The singularity is avoided not because we have found a clever mathematical trick, but because in this theory, the very structure of space-time itself makes it impossible. Space has a fundamental, unbreakable rigidity. It's not an infinite void that can be compressed to nothing. It is a quantum structure that resists annihilation. This provides a tangible physical mechanism for the bounce, transforming it from a philosophical concept into a concrete prediction of a leading candidate for a theory of quantum gravity. But even this elegant solution is fraught with its own challenges. The equations of loop quantum gravity are fiendishly complex, and producing a complete self-consistent model of a bouncing cosmology that also reproduces all the observed features of our universe. Its flatness, its uniformity, the specific patterns in the cosmic microwave background is a monumental task. Every prediction must be scrutinized, every parameter checked against astronomical data. For example, for the bounce to be successful and create a universe like ours, the preceding universe must have collapsed in a very smooth and uniform way. If it were lumpy and chaotic, with large variations in density from place to place, the bounce might have been uneven, producing a multitude of black holes instead of a new expanding universe. This introduces a new layer of fine-tuning. Not just the constants of nature, but the very state of the universe entering the bounce must be just right. So we are left with a grand and beautiful idea, shadowed by enormous theoretical challenges. The Big Bounce offers an escape from the ultimate beginning, a vision of an eternal self-renewing cosmos. It provides a potential explanation for the fine-tuning of our own existence. But it requires us to tame the relentless march of entropy, to invoke a new and unproven theory of quantum gravity, and to accept that the history of our universe may be written on a page we can never fully read. The work required to move this from a compelling story to a testable scientific theory is immense. It demands that we push our mathematical and observational tools to their absolute limits, searching for the faintest whispers from a time before time. So the blueprints are drawn, the equations refined to a crystalline edge. Theories of a universe before our own, once relegated to the fringes of philosophical debate, now stand as elegant mathematical structures. But physics is not mathematics alone. It is an empirical science, a dialogue with reality. And for any theory, no matter how beautiful, there comes a moment of reckoning. A point where it must step out of the abstract realm of human thought and present itself for judgment before the unforgiving tribunal of observation. For the Big Bounce to graduate from a compelling idea to a scientific reality, it must offer more than a solution to a singularity. It must have left a mark, a signature, an echo, however faint, of the cataclysmic collapse and rebirth that would have preceded our own cosmic dawn. The hunt for this evidence is the defining quest of 21st century cosmology, a search conducted not by looking forward into the future, but by peering back with unprecedented clarity into the deepest past imaginable. We are searching for a ghost in the machine of the cosmos. Our primary searchlight in this immense dark auditorium is a familiar character in our cosmic story, but one we must now see with new eyes. The cosmic microwave background. For decades, we have revered this faint, pervasive glow as the universe's baby picture, the fossilized light from just 3,800,000 years after the Big Bang. It represents the moment the cosmos cooled enough to become transparent, releasing a flash of light that has been traveling towards us ever since. The standard model of cosmology built on the Big Bang and inflation paints this ancient light as the afterglow of a singular explosive beginning. But what if that's not the whole story? What if the CMB is not a birth certificate but a layer of paint on an ancient canvas? A cosmic palimpsest where the text of a previous universe has been scraped away, but not so completely that a few faint traces of the underlying script cannot still be discerned by those who know how to look. The cosmologists hunting for the bounce are looking at this ancient sky with the meticulous focus of forensic investigators. They aren't interested in the CMB's near-perfect uniformity. They are obsessed with its tiny imperfections, its subtle variations in temperature. These anisotropies, amounting to differences of mere millionths of a degree, are the seeds of all cosmic structure, the primordial lumps from which all galaxies, stars, and ultimately we would grow. Inflation theory provides a powerful explanation for the general pattern of these seeds, a specific statistical distribution of hot and cold spots across the sky. For years, our observations from COBE to WMAP to the Planck satellite have matched the predictions of inflation with breathtaking accuracy. It is one of the great triumphs of modern science. And yet, if you look closely at the edges of this magnificent portrait, there are subtle oddities, anomalies, features in the data that seem just a little too strange, too coincidental to be mere statistical flukes. Theories of a contracting phase before the bounce make a startling prediction. The physics of that collapsing aeon, the way quantum fields behaved as the universe was squeezed into an ever denser state, would have left a very specific, indelible mark on the larger scales. Imagine the universe as a drumhead. Inflation in the standard model strikes this drumhead in a way that excites vibrations or modes of all possible wavelengths from the very short to the very long. But a bouncing universe is different. The long, slow collapse and the subsequent rebound act as a kind of cosmic filter. The physics of this era would have naturally suppressed the longest wavelengths, the lowest, deepest notes the universe could play. This would manifest in the cosmic microwave background as a curious lack of power in the largest angular scales we can observe on the sky. A mysterious quietness where inflation predicts there should be more activity. When cosmologists with the Planck satellite meticulously analyzed their data, they found something tantalizing. The data seemed to show a slight but persistent suppression of power at these very largest scales, just as some bounce models predicted. Is this a statistical fluke? A random hiccup in the cosmic data? Or are we seeing the first tentative acoustic shadow of a pre-existing cosmos? The evidence is far from conclusive, a mere whisper of a possibility, but it is enough to fuel a revolution. And then there is the infamous cold spot, a vast, unusually chilly patch in the CMB spanning over 1 billion light-years across. It is so large and so cold that according to standard inflationary theory, its existence is a profound statistical improbability. The odds of it appearing by chance are less than 1 in 1,000. It is an outlier, a puzzle that has vexed cosmologists for 2 decades. Explanations range from the mundane, a colossal supervoid, a vast emptiness between us and the CMB that has cooled the light passing through it, to the truly exotic. Some theorists, armed with bouncing models, have proposed a more radical origin. They suggest this cold spot could be a gravitational bruise, a remnant of a collision, a bubble of another universe that may have interacted with our own patch of space-time during the collapse phase. A scar left behind from the violent traffic of a much larger multiverse, visible only on the delicate skin of our infant cosmos. The debate rages on, a perfect example of the scientific process in action. Each new telescope, like the Simons Observatory being built high in the Atacama Desert, is designed to map these anomalies with even greater fidelity. They are pushing the boundaries of technology to answer a question that borders on the metaphysical, sifting through the noise of our own galaxy, the faint radio hiss of distant quasars, all to isolate a signal that has been traveling for 13.8 billion years. A signal that might tell us about what came before. But light, even light as ancient as the CMB, can only tell us so much. The early universe, before it became transparent, was an opaque fireball. Looking at the CMB is like looking at the surface of a dense cloud. We cannot see what lies within or what came before it. To penetrate that fog, to witness the bounce itself, we need a new kind of messenger, one that does not interact with matter, one that travels unimpeded from the most violent moments of creation. We need to stop looking at the universe and start listening to it. We need to hunt for primordial gravitational waves. These are not waves of light, but ripples in the fabric of space-time itself. They are the universe's own seismic tremors generated by the most cataclysmic events, merging black holes, colliding neutron stars, and most importantly, for our story, the very birth of the cosmos. Inflation, the violent superluminal expansion in the standard model, would have furiously shaken space-time, generating a powerful characteristic background of gravitational waves, a primordial hum, a static hiss that should still be echoing throughout the universe today. Finding this specific pattern of waves is the current holy grail for inflationists, a discovery that would almost certainly clinch a Nobel Prize. But bouncing cosmologies tell a different story. The gentler, slower contraction and expansion predicted by models like loop quantum cosmology, would have been far less violent in this regard. They would not produce the same furious storm of spacetime ripples. Instead, they predict a universe that is profoundly quiet in primordial gravitational waves. The absence of a signal in this case would be the signal. A great cosmic silence where inflation demands a roar. Here, then, is a clear, unambiguous test. A fork in the road. One path leads to a singular beginning, the other to an eternal cycle. All we have to do is build a celestial ear sensitive enough to hear the difference. This is without question one of the greatest technological challenges humanity has ever undertaken. The primordial gravitational waves we are looking for have been stretched by cosmic expansion for billions of years. Their wavelengths are now enormous, spanning light years. Their energy is fantastically diluted, making them unbelievably faint. Detecting them requires an instrument of planetary, even solar system proportions. This is the vision behind projects like the Laser Interferometer Space Antenna, or LISA, a titanic observatory not on Earth but in space. LISA will be a constellation of 3 separate spacecraft, flying in a precise triangular formation millions of kilometers apart. They will trail the Earth in its orbit around the Sun, a vast celestial net cast to catch the faintest tremors in spacetime. Each spacecraft will fire a laser beam at the others, constantly measuring their separation with a precision that is almost impossible to comprehend. If a primordial gravitational wave, a ripple from the dawn of time, washes through our solar system, it will minutely stretch and squeeze the distances between these spacecraft. The change in distance they will be designed to detect is less than the width of a single atom across a span of millions of kilometers. It is an engineering feat that demands perfection on an absurd scale, accounting for the gentle pressure of sunlight, the impact of cosmic dust, and the faint gravitational pull of every object in the solar system. LISA will be the most sensitive gravitational gyroscope ever built, a machine designed to feel the lingering pulse of creation itself. The teams of physicists and engineers working on this project are the modern-day equivalent of the cathedral builders of old. They are dedicating their entire careers to a project whose most profound data may not arrive until long after they have retired. They are driven by the sheer magnitude of the question at hand. And this hunt is not confined to one single experiment. Around the world, other projects are joining the search. Cosmologists are using the ultra-precise timing of distant pulsars, the rapidly spinning cores of dead stars, as a galactic-scale gravitational wave detector. These pulsars are nature's most accurate clocks, and by monitoring dozens of them, scientists can search for correlated jitters in their arrival times, a sign that a long wavelength gravitational wave is subtly warping the space between them and us. This pulsar timing array is a living, growing observatory, an instrument not made of metal and mirrors, but of the exotic remnants of stellar evolution, all woven together by theory and meticulous observation. Each data point collected over decades adds another pixel to the picture, slowly resolving the background hum of the universe. Will it reveal the hiss of inflation or the profound quiet of a bounce? The human drama behind this epic search is a story in itself. It is a world of fierce intellectual rivalries and deep collaborative friendships. Theoretical physicists who spend their lives in the abstract worlds of chalkboards and supercomputer simulations must find a common language with experimentalists who live in a world of cryogenics, vacuum chambers, and systematic error analysis. A theorist might spend 5 years developing a beautiful new model of the pre-bounce universe, a model that predicts a very specific quirky signal. Then, an experimentalist might spend the next decade of their life designing and building a machine capable of spotting that one specific quirk amidst the overwhelming cosmic noise, only to find nothing ruling the beautiful theory out. This is not failure. This is progress. This is how science, in its slow, methodical, and often frustrating way, grinds its way towards truth. It is a process of elimination, of testing beautiful ideas to destruction until the one that survives is the one that matches reality. We stand today at a thrilling precipice. The accumulated data from our telescopes has given us a standard model of cosmology that is fantastically successful, yet tantalizingly incomplete. And it is riddled with these curious anomalies, these loose threads that when pulled threaten to unravel the whole tapestry. The CMB cold spot. the suppression of power at large scales, the persistent nagging disagreements in the expansion rate of the universe, the so-called Hubble tension. Are these just cracks in our understanding, awaiting a more refined version of the standard theory? Or are they windows, glimpses, however fleeting, and distorted into a deeper, stranger reality? A reality where our Big Bang was not a beginning, but merely a transition, a moment of violent rebirth in an endless cyclical drama. The evidence is not yet in our hands. It remains hidden, encoded in the faintest variations of ancient light and the most ephemeral whispers of gravitational energy. But for the first time in human history, we are no longer just asking the question. We are building the machines powerful enough to demand an answer. The hunt is on, and its outcome will not just refine our textbooks, it will redefine our very sense of place and time in the grand cosmic narrative. For what we seek is not just the origin of our universe, but the ultimate context for our own existence. And so, after a journey to the very edge of space-time through the mind-altering physics of quantum foam and the speculative architecture of string theory, we are left here. We are left confronting a cosmos of breathtakingly different character than the one we thought we inhabited. The familiar story of a singular explosive genesis, a universe born from an infinitely dense, infinitely hot point, now faces a profound and elegant challenger. A challenger that doesn't erase the Big Bang, but reframes it not as a beginning, but as a transition. A single violent exhalation in an eternal cycle of cosmic breaths. This is the ultimate implication of the Big Bounce. It asks you to fundamentally recalibrate your understanding of the word origin. It suggests that the quest for a definitive starting line, a moment before which there was nothing, might be a misguided one, a limitation imposed by our own linear experience of time. Imagine for a moment letting go of that anchor. If our universe was not a one-time performance but merely the latest movement in an infinite symphony, then the 14 billion years we can measure are but a single note in an ageless composition. The starlight you see in the night sky, light from suns born billions of years after our universe erupted into being, could be carrying the faint residual echoes of a prior cosmos. The very atoms that constitute your body, forged in the hearts of stars, might be reconstituted matter and energy from a universe that existed before our own, a universe that lived, expanded, and died its own cosmic death only to be reborn, phoenix-like from its own ashes. This concept shatters the wall of our cosmic horizon. It transforms the singularity, once seen as an absolute beginning, into a permeable membrane, a gateway between cosmic epochs. Our universe didn't just appear from an unknowable void, it could have inherited its existence. It may carry a cosmic DNA, a set of physical laws and fundamental constants passed down through the crucible of the bounce itself. The search for our origins is no longer about looking back to a single point. It becomes an act of cosmic archaeology, sifting through the fabric of our own reality for the fossilized remnants, the telltale signatures of a parent universe. This vision forces an even more unsettling reckoning, a confrontation with the nature of time itself. We experience time as an arrow flying inexorably from past to future. This arrow is intrinsically linked to entropy, the universal law that dictates a relentless slide from order to disorder. A broken glass does not reassemble itself. An old star does not grow young again. The standard cosmological model honors this. It begins in a state of supreme order and ends in the potential chaos of a big rip, or the cold, dark emptiness of heat death. It is a story with a definitive beginning, a middle, and an end. But the Big Bounce turns this linear narrative into a circle. If the universe can rebound, it must possess a mechanism to reset its own entropic clock. The collapse leading to a big crunch or the quantum transition that circumvents the singularity must be a moment of cosmic renewal, a process that launders the disorder of a dying cosmos and prepares it for a new era of structure and complexity. Time in this framework is no longer a finite resource. It is boundless, stretching infinitely into the past and future. What does causality mean in such an eternity? If there was a cosmos before ours, were its inhabitants, if any, our ancestors, is information from one cycle preserved even in a scrambled form into the next? Or is each bounce a complete reset, cosmic amnesia, where the universe forgets itself entirely, only to rediscover consciousness, life, and intelligence a new aeon. After agonizing beautiful aeon, the questions themselves reshape our perception of reality. They suggest that the universe is not just a stage for existence, but a participant, a living, breathing entity whose metabolism spans trillions of years, whose life cycle makes the lifespan of stars seem as fleeting as the blink of an eye. Our journey to this point has been a testament to human audacity. We began with ancient myths, stories of creation from chaos or darkness, primitive attempts to answer the fundamental question, where did all of this come from? We progressed to the careful observations of astronomers like Hubble, who revealed a universe far larger and more dynamic than we ever dreamed. A universe in a state of dramatic, accelerating expansion. This discovery gave birth to the theory of the Big Bang, a monumental achievement of 20th century science, a story of our origins that was for the first time grounded in mathematics and physical evidence. For decades, it has been the bedrock of cosmology, the grand narrative that explained the cosmic microwave background, the abundance of light elements, and the very structure of the cosmos. Yet even the greatest theories have their limits, their points of failure. The Big Bang Theory, for all its power, falls silent at the moment of creation. It leads us to the singularity, a point of infinite density where the laws of physics as we know them break down completely. It presents us with a wall, and on that wall it simply writes, "Here magic happens." It took a new generation of thinkers, armed with the strange and powerful tools of quantum mechanics and string theory, to dare to ask what lay beyond that wall. They refused to accept an unknowable beginning. They saw the singularity not as an answer but as a question. They proposed that the breakdown of our equations wasn't a failure of the universe but a failure of our description of it. By weaving together Einstein's relativity with the probabilistic world of the quantum, they found a way to smooth out that infinite point, to replace the cosmic brick wall with a gravitational trampoline. This intellectual leap from a finite beginning to an infinite cycle represents one of the most courageous shifts in scientific thought. It is a move away from the comfort of a creation story and toward the dizzying vertigo of an eternal existence. We must, however, walk this path with profound intellectual humility. The Big Bounce is not, as of now, a proven fact. It is a hypothesis, a beautiful and compelling mathematical ghost haunting the machine of modern cosmology. It lives in the elegant equations of loop quantum gravity, in the multidimensional ballets of the ekpyrotic model, but it has yet to leave an unambiguous signature in our telescopes. The evidence we would need to confirm it is fantastically difficult to obtain. We are searching for a whisper from before the Big Bang, an echo of a cosmic cataclysm that predates our own universe's birth. This evidence might be hidden in the subtle patterns of polarization in the cosmic microwave background, the afterglow of our own hot beginning. Perhaps specific types of primordial gravitational waves, ripples in space-time generated by the bounce itself, still propagate across the cosmos, waiting for detectors sensitive enough to hear their faint song. Or perhaps the evidence is forever beyond our reach, erased by the sheer violence of the cosmic rebirth, leaving the bounce as a tantalizing, untestable piece of philosophy. Many physicists remain deeply skeptical, and for good reason. Science advances not on the beauty of its ideas, but on the cold, hard currency of evidence. Without that evidence, the Big Bounce remains a speculative frontier, a bold what-if posed to the cosmos. It stands as a powerful reminder that our most advanced theories are still just maps, and the map is not the territory. The true territory of the universe may be stranger, more complex, or even simpler than our current imagination can conceive. But even as a hypothesis, its power is undeniable. It offers a vision of the universe that is for many deeply resonant. The standard model, with its potential endings in a lonely, cold, dark, or a violent tearing apart of space-time, can feel nihilistic. It presents our cosmic moment as a brief flicker of warmth and light in an otherwise bleak and finite existence. The Big Bounce, in stark contrast, offers a story of cosmic resilience. It portrays a universe that is fundamentally indestructible, a system that renews itself, that learns from its collapses and expansions endlessly, experimenting, endlessly creating. There is a profound, almost spiritual elegance to this idea. It replaces the concept of a singular, miraculous creation with a process of eternal, natural transformation. Our universe is not a fragile exception, it is a part of an unending, self-sustaining reality. This vision transforms our relationship with the cosmos. We are not the improbable inhabitants of a one-time event. We are the children of an eternal cycle, the current custodians of a universe that has lived countless lives before this one and will live countless more after we are gone. It suggests that the emergence of complexity of stars, planets, and life is not a fluke, but an integral part of the cosmic rhythm. The universe in this picture is not destined for death. It is destined for rebirth. And this is where we leave you. Not with a final answer, but with a grander, more profound question. The quest to understand our ultimate origin is far from over. The ideas we have explored represent the absolute cutting edge of human thought, the frontier where physics, mathematics, and philosophy meet. The final chapter of this story will not be written by us. It will be written by a future generation of explorers, by the scientists, engineers, and dreamers yet to come. They will have new tools at their disposal, telescopes that can see deeper into the dawn of time, particle accelerators that can probe the nature of energy and matter with a precision we can currently only dream of, and theories of quantum, gravity that may finally unite the very large and the very small into a single coherent picture. They will stand on the shoulders of the giants we have discussed, and they will push the boundaries of knowledge even further. Perhaps they will find the definitive proof of the bounce, confirming that we are part of an infinite cosmic ocean. Or perhaps they will discover something else entirely, a new and unexpected truth about our origins that is even more astonishing. The ultimate value of an idea like the Big Bounce is not whether it turns out to be right or wrong. Its value lies in its power to expand our minds, to force us to question our most basic assumptions, and to inspire us to look up at the vast, silent darkness with a renewed sense of wonder and a burning curiosity. It is the engine of discovery. The story of the universe, whether it had a beginning or not, is our story, and the search for its truth that is perhaps the most noble journey we can ever undertake.